termed Smoky Death Trap, Soviet casualties of the space race, a plane that drops mysteriously from the sky, a car that ignites on impact, tragic blunders, or inevitable missteps on the path to progress. Now, Engineering Disasters 4 on Modern Marvels. From Egyptian pyramids, to medieval castles, to 21st century skylines, the world has been shaped by engineering feats of dazzling invention. But progress comes with a price. When exploring the unknown, disasters are often an inevitable and valuable prelude to success.
The entire process of design theory development has come to a great extent from lessons experienced through trial and error.
Few modern venues are as well suited to calculate the odds of success than the glittering hotel casinos of Las Vegas. So when local firefighters received an alarm from the MGM Grand Hotel on November 21st, 1980, they figured the call was routine.
It has fire protection systems in place, and it's a brand new building, so you're kind of bored by the whole affair. We made a right-hand turn where we could actually see the MGM, and it was like an A-bomb went off.
As more fire companies were called to the scene, the blaze at the ground floor casino was roaring out of control. Hundreds of hotel guests were trapped on the floors above by rising smoke.
You could see people up there 100 yards away, and they were in fear of their lives.
A lot of them had very little clothes or whatever they had with them. Some of them had towels over their face. You could see a lot of them had breath, taking in some smoke. So they were definitely running for their lives.
But the MGM fire was a tragedy that could have been avoided. It was a disaster whose genesis began with flawed engineering and was later compounded by poor maintenance and bad luck. When the MGM opened on the Vegas Strip in 1972, fire codes called for sprinkler systems throughout the 27-story building and T-shaped guest tower. But an exception was made for the MGM's ground floor casino and an adjoining deli restaurant. Since both were open 24 hours a day, it was decided that any fire that broke out in those areas could be quickly contained. Sometime after the hotel opened, however, the casino's deli restaurant began closing at midnight. Early on the morning of November 21st, a fire started in an enclosed area of the restaurant that was used for bussing dishes, known as a side station. Investigators built this full-scale reproduction of the side station to trace the movement of the fire and filmed the blaze.
The delicatessen side station had a 2-foot by 2-foot air transfer grill located in its ceiling. As a result of this, the fire could develop in that space undetected and develop to the point that we know as flashover, which makes it much more hazardous.
Flashover is the point at which virtually everything that's flammable within an enclosed area starts to burn. Once the fire reached flashover in the deli restaurant, it roared into the casino, which was filled with combustible furnishings, 12 tons of glue in the ceiling tiles alone. Meanwhile, a flawed air control system allowed smoke and carbon monoxide to sift upwards toward the top levels of the guest towers.
There were a number of shafts within the building, the elevator shafts, the stair shafts, in addition to the ventilation system. And so it was people actually on the uppermost floors that were subjected to the most severe smoke conditions.
The interior exit stairwells became the most dangerous places of all, escape routes that turned into death traps.
There was smoke coming up some of the stairways, and when people tried to leave the stairways because of the smoke, they found that the doors from the stairway side had been locked for security purposes, and they couldn't get out of the stairways on any floor.
One firefighting device in the hotel worked perfectly: the sprinkler system. The areas without sprinklers, the casino in Delhi, became charred ruins. But sprinklers kept the fire from spreading elsewhere.
Anywhere there were sprinklers, the fire stopped in its tracks. The sprinklers themselves put it out without any help from firefighters or whatever. It went out right there.
That's like the untold story and the whole affair. If that building didn't have a sprinkler system, it would have burned from top to bottom, side to side. The whole building would have burned.
The MGM Grand Fire ultimately claimed 85 lives, the second most deadly hotel fire in American history. The tragedy sparked a massive reform of fire protection systems, starting in Las Vegas.
Control to Unit 6. Respond down to Central Plant. We got a trouble with the smoke detector down there.
Today, Bally's Hotel stands on the site of the former MGM Grand. It boasts a state-of-the-art system designed to foil any fire in its tracks, starting at the Fireproof Command Center.
This system monitors over 12,000 points here at Bally's. We have over 1,800 smoke detectors throughout the hotel. We also monitor all the sprinkler flow systems, also any control valve associated with the sprinkler system.
If a fire signal comes to the command center, elevators can be automatically shut off or rerouted to safe areas. Phone jacks at all floors allow instant communication with firefighters, and interior stairwells, the notorious fire traps in the MGM Grand Blaze, are pressurized and equipped with air blowers to create smoke-free zones for escape.
Stairwells and the towers are going to pressurize. That keeps smoke out so people can get in to the hallways, get into the stairwells, and that's an area of refuge that they can use to get down to the ground level and get out of the building.
Sprinklers are installed at 10-foot intervals or less throughout the hotel, including the cavernous casino at Ground Zero. The sprinklers are a reminder that even in modern high-rise buildings, most fires are best contained when water is easily at hand.
Between 20 to 24 gallons per minute will come out of these heads, and that's quite a bit of water in anybody's terms. It'll put a serious hurting on a fire.
Despite the engineering flaw of omitting sprinkler systems in the MGM's casino and restaurant, that fire might still have been contained if detected sooner. But the 1987 collapse of the partially constructed L'Ambiance Plaza Towers in Bridgeport, Connecticut, an avalanche of concrete and steel which killed 28 construction workers, unfolded in an instant.
This was a collapse that happened without any warning. The buildings just took off and crumbled.
Designed in the early 1980s as two connecting 16-story towers, L'Ambiance Plaza was intended to provide affordable housing in downtown Bridgeport. To set the floors in place, engineers proposed using the popular lift slab technique, a method prized by builders for both economy and safety.
The advantage of the method from a safety point of view is all of the concrete work is being done at the ground level rather than working high in the building.
To pull the slabs up from the ground, steel collars called shear heads framed the openings in the floor slabs around the steel columns. The slabs are then hoisted by lifting rods, each of which is attached to a large nut that fits under a component of the shear heads, known as the lifting angle. The slabs are then jacked up to resting locations, where they are supported by temporary wedges, tack-welded into the columns. The vertical pressure exerted by the weight of the slabs keeps the nut and the wedges in place.
Those wedges are nothing else but loosely put in wedges. They are not held by anything else, friction. The assumption is that that nut is going to sit there transferring the vertical load and is not going to shift horizontally, where that assumption apparently is not as reliable as people have thought.
The 2,900-ton slabs at L'Ambiance were hoisted 3 at a time from ground level. Investigators believe that the accident began when a lifting angle in one of the shear heads deformed, causing the nut underneath to slide out, instantly destabilizing the lift slab operation.
that the nut has slid out, and then we are unsupported. More weight is dumped to the other columns, the slab starts breaking, and the entire thing collapses.
Deficient welds used in the construction of the shear heads may have eroded support for the slabs as well. Once the slabs began falling, the weight of 3 concrete units, close to 9,000 tons, created a pancake effect on the floors below. The lift slab technique also depends on the stability of its surrounding structure. But when the accident at L'Ambiance Plaza occurred, construction of those walls lagged several stories below the area where the slabs were being raised. Without the presence of surrounding walls to provide lateral stability, a localized accident became a scene of massive destruction.
When the failure occurred, there were many thousands of tons of concrete raining down to the ground in a very short time. So that was, of course, very catastrophic.
The totality of the L'Ambiance Plaza collapse made it difficult for investigators to pinpoint the triggering cause with absolute certainty. But following the disaster, the state of Connecticut banned lift slab construction on all high-rise buildings. While it remains legal elsewhere, the lift slab method has been almost entirely abandoned, underscoring the magnitude of the tragedy at L'Ambiance Plaza. 28 people died there, making it one of the most fatal construction accidents in American history. In 1957, the Soviet Union successfully launched its Sputnik into Earth orbit. The satellite's success turned outer space into a Cold War battleground between the Soviet Union and the United States.
The space race really was an offshoot of military need. I mean, both the rocket that launched Sputnik was really initially an ICBM. It was designed to send a nuclear bomb to the United States.
But for the Soviet Union, the high-stakes race to gain the upper hand in military might would lead to the most fatal rocket disaster in history. By the fall of 1960, presidential candidate John F. Kennedy was charging that America was on the short end of a missile gap. At the same time, Soviet Premier Nikita Khrushchev was boasting of his own country's overwhelming missile strength. In reality, the Soviets lagged far behind.
Khrushchev gave a speech in which he said that we're building these rockets like sausages. So the West believes the Russians have a lot of ICBMs. Well, in truth, they really didn't. They had this really poor ICBM called the R-7, which didn't work very well. So they were really hurriedly trying to develop a second one called the R-16.
As the Soviets prepared for the test launch of their 2-stage R-16 missile in October of 1960, Khrushchev ratcheted up the pressure. He dispatched his chief designer, Mikhail Yangel, and his missile troop commander, Field Marshal Mitrofan Nedelin, to the launch site, adding political pressure to an already tense and uncertain operation.
This is about the Cold War. We need this missile. So this sort of pressure goes down from every level, down from Khrushchev, down to Nedelin, the commander, down to the chief designer Yangel, down to his engineers, down to the soldiers. Everybody knows this is a big deal.
Initially set for October 23rd, the R-16 launch was delayed when major fuel leaks were discovered in the 2-stage rocket. But instead of following standard safety procedures, Field Marshal Nedelin ordered the rockets repaired without draining the fuel tanks, a calculated gamble to save time. Engineers were still working on the rocket the next day as the countdown began. But 30 minutes before the scheduled 9 p.m. launch, a spurious communication signal prematurely activated the rocket's second stage.
The engine ignites, the fire goes into the first stage, which is packed with toxic propellants. The first stage explodes. Immediately there's a gigantic fireball. Hundreds of tons of toxic propellant have just exploded.
A camera set up to record the launch captured the horrific scene. As hundreds fled for their lives, those standing close to the rocket, including Field Marshal Nedelin, were instantly incinerated. At its apex, the temperature of the fire reached 3,000 degrees, melting everything in its path. Over 150 people died, including many top Soviet scientists and engineers. But for decades afterwards, the story of the disaster remained hidden from the public.
It wasn't even acceptable to admit that this happened. It was you would be violating state secrecies. So people who were mourning for their relatives couldn't officially, openly mourn.
6 months after the R-16 disaster, cosmonaut Yuri Gagarin became the first man to successfully orbit the Earth. To all outward appearances, the Soviets were capturing the high ground of space.
Yuri Gagarin goes up into space in April 1961. He's the first human being in space, which is, of course, a great accomplishment. But, it wasn't balanced by the tragedy of 6 months prior.
Responding to Gagarin's success, President Kennedy issued a challenge of his own, setting into motion a space race that would result in one of America's greatest technological triumphs.
This nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
As the United States made step-by-step progress toward that goal, marking well-publicized failures as well as triumphs, the Soviets embarked on a clandestine program to reach the moon. But inferior technology and official secrecy doomed their bid to compete.
Part of the problem of Soviet Union that they tried to get to the moon with a hand file and a hacksaw. The other aspect was the pressure from politicians and the level of secrecy that that system required.
What the Soviet system produced was the N-1, an enormous three-stage rocket 330 feet tall and propelled by 30 engines.
It's so big that American spy satellites can see it very nicely on the pad. They know that it exists, even though the Soviets haven't publicly announced all this.
In the summer of 1969, as the U.S. prepared to launch Neil Armstrong, Buzz Aldrin, and Michael Collins to the moon, the Soviets were still hoping to stay in the race by sending an unmanned N-1 rocket on a moon mission.
Their whole plan was, we're going to fly the super booster, it's going to go around the moon, it's not going to have a crew on board, but there is a lot of anticipation, it's like a real race.
On July 3, 1969, the N-1 took off as scheduled from the launch pad. But just after liftoff, a misfiring engine set off a chain reaction that sent the rocket to a fiery doom.
The thrust is mismatched, the rocket starts to swerve a little bit, and it's only raised a few hundred feet above the pad. And eventually, the computer command basically shuts down all the engines. The rocket, of course, slowly comes back down on the pad, just explodes in a massive explosion. And it's probably the biggest explosion ever in the history of rocketry.
Although no one was hurt in the N-1 rocket disaster, the Soviets made just 2 more failed attempts to launch the rocket before abandoning the N-1 mission for good. It was a program at once propelled and doomed by the secretive system that surrounded it.
There wasn't much exchange within the Soviet Union. The failures that they had were not discussed. You discuss the failure, you were accused of treason.
As the Soviet Empire began to crumble in 1989, details of the N-1 rocket and R-16 missile failures finally came to light. By that time, the Soviet space station Mir was well established.
One could say that the failures of the moon program eventually led them to this space station path, which became Salyut, then became Mir, and then eventually is now the International Space Station.
But if Mir was a triumph of Soviet technology, its development was due in part to the abandoned schemes of decades past. The Point Pleasant Bridge, which spanned the border between southern Ohio and West Virginia, was filled with commuters and Christmas shoppers on the afternoon of December 16, 1967. Suddenly, the bridge collapsed, sending dozens of cars and passengers into the frigid waters of the Ohio River. The death toll would ultimately reach 46, the worst loss of life from a bridge accident in American history.
The bridge was built in 1928, and it came down in 1967. One has to ask, how could a bridge exist for almost 40 years and then all of a sudden collapse?
The mysterious collapse of the Point Pleasant Bridge can be traced to its unusual construction nearly 4 decades earlier. Unlike classic suspension bridges like the Golden Gate, which are linked by hundreds of wound steel cables, Point Pleasant's construction was of a type similar to Pittsburgh's 6th Street Bridge, which was constructed at the same time, and whose suspension depended on parallel chains of steel eye-bars.
Each end of the eye-bar are holes through which pins are passed. So it's a series of straight links that are pinned to articulate and achieve more or less the curve of a suspension bridge.
It was very strong material. This allowed them to build the bridge in a very light fashion so that they could have long, lightweight elements in the bridge.
Coated with shiny aluminum paint, Point Pleasant became known as the Silver Bridge, an elegant and aesthetically pleasing structure 1,460 feet long. But unlike the cables of a traditional suspension bridge, the Silver Bridge eye-bars provided no redundant means of support. Instead, they formed a chain, which proved to be only as strong as its weakest link.
If one significant part fails, the entire bridge will collapse. I don't know when that concept became well known, but it must not have been practiced in the 1920s.
After examining the wreckage from the Ohio River, a team from the National Bureau of Standards, now known as the National Institute of Standards and Technology, created this model of the Silver Bridge. They determined that the fatal fissure occurred at one end of eye-bar number 330, the result of a 1/8 inch crack caused by decades of corrosion. When the eye-bar finally broke, the force of the fracture loosened the connecting pin in the joint where the break occurred, allowing the other eye-bars to slip out, breaking the chain of suspension, dropping the roadbed, and collapsing the bridge.
This is where the brittle fracture occurred. Actually, it's been removed for microscopic examination, but it was very flat, just like this.
The Silver Bridge eye-bars were made of heat-treated medium-high carbon steel, an unusually strong but brittle metal that is susceptible to cracking from natural corrosion. But the covered joints where the fatal fracture occurred were concealed from view during routine inspections of the bridge.
The last real inspection was back in 1951. Apparently this was done by someone looking at the bridge with binoculars from the ground. So again, we have a maintenance problem for sure.
The collapse of the Silver Bridge led to a systematic inspection of bridges throughout the country for the first time in U.S. history. Many older bridges were either dismantled or retrofitted to meet new safety guidelines.
There was a general looking at bridges to examine their redundancy and their susceptibility to this kind of failure. It certainly had an impact on all future bridges that were built, so they never built one like this again.
Oversights in maintenance procedures were also to blame in the collapse of the world's first floating concrete bridge. Built in 1940 in Seattle, the Lacey V. Murrow Bridge was named after the director of Washington State's Department of Transportation. The bridge stood for 50 years, but in November of 1990, a rehabilitation and maintenance operation on the bridge led to disaster. Spanning a short but deep section of Seattle's Lake Washington, the Murrow Bridge floated on a row of 25 hollow concrete pontoons, each 350 feet long. The pontoons were bolted together for stability and anchored to the bottom of the lake.
The conditions are just right for use of such a structure because the water conditions under which they're installed are perfect. That is, very seldom is there any ice, very seldom is there a heavy current, and the water is very deep, 200 or more feet.
In the fall of 1990, the Murrow Bridge was undergoing a facelift by means of hydrodemolition, a process in which highly pressurized water is used to break up the roadway. Since environmental regulations prohibited dumping the contaminated water into the lake, it was temporarily stored in the empty pontoons via access holes which were cut into the tops and sides of some sections. The water level inside the pontoons was carefully monitored so the structure would not be compromised. But on Thanksgiving weekend, with bridge crews short-handed, a heavy storm hit the Seattle area. Rainwater drained into the open pontoons. Winds from the storm whipped up the surface of the lake, propelling splash water into the pontoons as well. On the morning of November 25th, 8 waterlogged pontoons sunk into the lake, taking those sections of the bridge down with them and severing 12 anchoring cables of a bridge that was being constructed nearby. While luckily no one was injured, the cost of damage was estimated at $69 million. An investigation of the accident came to a sobering, if unsurprising, conclusion.
After very extensive study and very sophisticated computer modeling methods, the conclusion was that concrete pontoons simply don't float when they're full of water. A very unsophisticated mode of failure.
The Lacey V. Murrow Bridge was rebuilt 2 years later. Though it looks the same from the outside, the pontoons that support the bridge have been divided into smaller sections to minimize damage from leaks, a precaution that underscores the structural similarities between floating bridges and floating ships.
The pontoons were designed with multiple cells, not unlike the multiple cell supertankers, so that failure in one place would not bring down the entire pontoon.
What has happened here, they simply had a ship in which they made a hole in the hull and they put it in the water. Well, the ship filled with water and sank. That's what the bridge was all about.
The Lacey V. Murrow Bridge collapse caused no deaths or injuries, but it provided a dramatic reminder that no engineering feat remains entirely immune from the forces of nature.
Why I spent an inordinate amount of time on the Corvair. It is because the Corvair is an inordinately dangerous vehicle.
In the summer of 1966, a Senate subcommittee chaired by Robert Kennedy and Abraham Ribicoff held hearings on the need for auto safety regulation. Among those testifying was a young attorney named Ralph Nader, who took dead aim at a popular compact car called the Corvair. Introduced in September of 1959, the Chevrolet Corvair was the first air-cooled, rear-engine automobile mass-manufactured in the United States. The car was a hit with the public. Sleek and sporty with an innovative unit body construction, the Corvair seemed a perfect match for the effervescent mood of the emerging 60s.
It was a sort of a happy time. There was a youth market now that had a craving to have their own cars as well.
It's way ahead of its time for many reasons. It's a rear-engine car, which was a first, with an air-cooled engine in the guise or genre of Porsche automobiles. Even to this day, it had outstanding styling.
But the Corvair's rear engine contributed to a weight disparity between the front and rear ends of the car, making the Corvair unpredictable to control in sharp or sudden turns.
The rear end of the car would swing out to its left, and the car would want to be making a tighter circle, in other words, than what the driver was intending and even what the driver was perceiving. And suddenly the driver would recognize, oh my God, the rear end of the car is swinging out, and the person driving the car would hit the brakes, which would make the situation worse.
To correct the steering problem, the Corvair owner's manual specified radically different tire pressures for the front and rear wheels. 26 to 28 pounds per square inch in front, and just 15 psi in the rear. It was advice that many owners routinely overlooked. But critics like Nader claimed the Corvair's control problems were exacerbated by the car's swing axle rear suspension. During sharp cornering, it was alleged that the vertical angle of the rear wheel, or camber, would tuck under so sharply that the car was prone to a rollover.
The tucking under of one of the rear wheels, then the steel wheel rim would gouge into the pavement and would serve as a tripping mechanism.
The publicity surrounding the Kennedy-Ribicoff Senate hearings helped shift popular opinion against the Corvair and in favor of legislation to establish uniform auto safety standards. One result was the creation of the National Highway Traffic Safety Administration, NHTSA, to set regulations for passenger vehicles, trucks, and school buses sold in the United States.
The legislation that came about from these congressional hearings said to the auto industry, you cannot any longer make and market whatever you feel like, but there have to be federal safety standards to which you must comply in each vehicle that you intend to sell to the public.
In 1966, the year of the Senate hearings, sales of Corvairs dropped dramatically. But the demand for smaller, fuel-efficient vehicles continued to grow. So in 1970, Ford introduced the Pinto, a car initially targeted to weigh 2,000 pounds and to cost $2,000.
The Pinto was basically a scaled-down version of a regular-sized car, but in order to keep the cost low and the weight low, the Pinto was rushed into production without paying much attention to the vulnerability of the fuel tank.
Located 3 inches from the rear bumper, the Pinto fuel tank was easily ruptured in a low-speed rear collision. The gasoline filler tube, welded by screws to the fender but not to the tank, often fell out on impact. Protruding bolts and edges from the differential and rear suspension could puncture the fuel tank's thin sheet metal. The spilled gasoline could easily ignite. Also, the impact of a collision could jam the doors shut, trapping victims inside. This test by the National Highway Traffic Safety Administration, in which a Pinto was hit from behind at 35 miles per hour, showed just how dangerous the car could be.
It was a total disaster in terms of an unsafe fuel tank, an unsafe filler tube, minimal rear body structure, doors that would jam. Everything was bad about the Pinto in a rear impact.
Horrifying burn accidents from rear-end collisions made the Pinto notorious. Following their own crash tests, NHTSA set tougher legal safety standards for rear-end collisions. In 1978, Ford recalled 1.4 million Pintos for safety improvements. But by that time, the Pinto's reputation was beyond repair.
When you start producing something that millions of people are going to use, the consumer has expectations, and if you don't meet those expectations, there is somebody else that is going to satisfy them, and the consumer is going to forget your name very fast.
But the story of the Pinto was also a matter of missed opportunity. In Ford's early crash tests of prototype Pintos, some were equipped with airbags and a plastic bladder liner inside the fuel tank.
This is a fuel cell bladder, and right next to it, this is an actual Pinto fuel tank, and inside is such a bladder liner, a safety bladder liner. Now, Ford Motor Company crash tested Pintos with a similar safety bladder liner inside the sheet metal fuel tank, and in their crash tests,
even though the sheet metal fuel tank was punctured in what Ford said are puncture-prone areas, thanks to the safety bladder liner inside the fuel tank, there was no leakage.
However, both the airbags and the fuel cell bladder had been eliminated to save money by the time the Pinto hit the highway.
It would have had airbags, it would have had a safety fuel tank, it would have been the safest small vehicle ever made, and it would have been a true engineering marvel rather than a profound engineering disaster.
Jet travel is a familiar feature of the world in which we live. But it was a barely imaginable luxury when the world's first scheduled commercial jet, the Comet, took off from England's Heathrow Airport in May of 1952. The Comet was a pioneer plane that changed the world. It was also a craft with a fatal flaw. Comet development began during the darkest days of World War II. As England struggled to survive the war, engineers at Britain's de Havilland Aircraft Company were designing a revolutionary plane for the peace to follow. Airline industry experts claimed that commercial propeller planes would never be supplanted by jet aircraft when the Comet debuted in 1952. But by cutting air travel time in half and affording more comfort, the Comet was a hit, and it became a symbol of national pride for a country so recently ravaged by war.
The Comet proved to the world that jet commercial aviation was the way to go. It was higher, faster, safer.
So the passenger said, well, I can get there in half the time, it's smoother, I'm going above the weather, this is for me.
Along with convenience, the Comet introduced far-reaching innovations for civil aircraft, including the now standard swept-back wing design. It was the first commercial plane to utilize a rapid underwing refueling system, and the first to bleed air from the engines to pressurize and heat the interior, a major advance from propeller planes.
People had used furnaces and pumps to pressurize and heat the interior, and they were a source of carbon monoxide poisoning and accidents that had happened. And the Comet got around that by using bleed air from the jet engines. Now, of course, you say, well, that's obvious. But it wasn't. It was the first time it was done.
The Comet's fuselage, composed of a metal alloy, was light enough to carry 36 passengers at 500 miles an hour, yet strong enough to keep the cabin comfortably pressurized even at 40,000 feet. The plane's polished aluminum exterior and distinctive rectangular windows showed off de Havilland's unique sense of style, a flourish that would carry a cost.
There used to be a saying at de Havilland, and if it doesn't look right, it isn't right. Well, the airplane looked right, and it was very right.
For 2 years, the Comet flew passenger routes throughout Europe, Africa, and Asia. But like its namesake, the Comet's reign would be dazzling but brief. A 1953 crash on takeoff was blamed on pilot error. Then, in the spring of 1954, 2 comets fell from the sky without warning over the Mediterranean Sea, killing all aboard. England went into shock. Winston Churchill called on the Royal Air Force to retrieve pieces of the Comet from the sea and to search for clues to the mysterious disaster. The commercial Comet fleet was grounded. To discover the cause of the crashes, engineers immersed a Comet in a water tank and simulated the cyclical stresses of its performance in the air. The tests showed that the Comet fuselage experienced metal fatigue at a rate relatively equal to the number of hours which had been flown by the 2 doomed jets. The Comet's weakest stress points were at the corners of the plane's rectangular windows. When the windows cracked at 30,000 feet, the result was instant decompression, an explosion from within.
Fatigue has to derive from some initiating anomaly. In the case of the Comet, it was a very sharp corner in a window which created a stress concentration, which we know nowadays sharp corners are an anathema to any structure carrying load.
But the Comet's journey was far from over. In 1958, de Havilland introduced the Comet 4, a bigger, stronger version of the original passenger plane, including reinforced oval windows. The Comet 4 promptly made headlines by becoming the first passenger jet to cross the Atlantic. Meanwhile, the lessons learned from the crash of the Comet 1 were shared with rival companies like Boeing, whose larger 707 jets would dominate the next era of commercial flight.
The lessons of the Comet were being passed to the United States designers at all times. They were in contact. There was no commercial secrecy going involved. The aviation industry was too interested in getting the jet airliner right.
The Comet 4 became a dependable carrier for the next 20 years on airlines throughout the world. Determined not to repeat the mistakes of the past, the plane set high standards for structural stability and piloting precision.
You could touch down as lightly as a feather. It was very precise. It stopped well. It steered well. It was nice. It was just a lovely airplane.
Today, at the Museum of Flight's hangar near Everett, Washington, Bob Hood is organizing a restoration of a Comet 4. It's a plane whose innovations are still utilized by jets today, from the redundancy of its hydraulic systems to its development of the now standard four-wheeled landing gear.
I think we want people to know 50 years from now, at some undetermined point from now, what the first jet airliner was like.
In an age where jet travel has become commonplace, the Comet holds a place in history as the plane that started it all. And the lessons imparted on its watch, in triumph and in tragedy, shaped the world we inhabit today.
I would equate it with the Wright brothers at Kitty Hawk, quite frankly, because its implications were as much, if not more, in terms of transport and opening up the world.
Planes and cars and bridges, high-rise hotels and high-flying spacecraft, all have drawn lessons from the failures of the past.
Structural engineering is the art and science of molding materials we do not fully understand into shapes we cannot precisely analyze, to resist forces we cannot accurately predict, all in such a way that the society at large is given no reason to suspect the extent of our ignorance.
Technological progress follows an unpredictable path, one which invariably strikes a balance between human ideals and human imperfection.
We go and we look at structures, how they failed, why they failed, how they collapsed, and we improve. So failures play an extremely important role in the progression of technology.